So the first speaker of this afternoon is Mariana Gonzalez, and she's going to tell us about the double copy in Mini-Twistor space.
Well, hello everyone, and thanks for the invitation to speak at this workshop. It's very interesting. So my topic is probably going to be a bit different from what you've been hearing. And the first half is going to be just explaining what double copy is, some of the basics, and a little bit of a review. And the second time, I'll go into what Mini-Twistor space and how you can see this squaring relation there. So let me just start with a broad introduction of why we care about this. So the main goal is understanding gravity better. As we know, gravity can be highly nonlinear, which makes many calculations complicated. For example, if you want to do scattering amplitudes, we know you have infinite number of vertices that can give you a very complicated calculation of your S matrix. Also, it can be very hard to construct non-perturbative solutions, again, from its very highly nonlinear nature. But these nonlinearities also help you to have interesting phenomena like horizons in black holes or in the ether, for example. But there are many ways that now we have to understand gravity better, and some of the most successful ones are through dual descriptions. For example, the ones we know well in holography, like in ADS-CFT, and newer proposals that try to understand these holographic descriptions, either for flat space or for the ether. But here I'm going to talk about a different kind of duality that's called color-kinematics duality, and it arises in the double copy, which basically is the idea of writing gravity as some sort of square of a gauge theory. So let me just give you a short review and introduction of what we call color kinematics duality and what this squaring procedure is. So we're going to be looking at the scattering amplitudes, starting with a Yang-Mills field here. And these scattering amplitudes can be written as a sum over trivalent graphs, where I'm going to split color and kinematics in different areas. These CIs are called color factors, and they depend on structure constants of your group. Think of SUN, for example. And the NIs, on the other hand, are kinematics, so they depend on momenta or the polarization vectors of your Yang-Mills. Here in the denominator, you will have just multiplication of propagators that arises in your amplitudes. So first of all, we can think of massless theories in Yang-Mills, so it would be just like multiplication of p squared. Now, from Yang-Mills and from the group structure of Yang-Mills, we know that the color factor has some algebra that it will satisfy. For example, a Jacobi relationship between structure constants that schematically will look like this. The big insight in 2008 of Bernd, Carrasco, and Johansson is that the kinematic part, when you write the amplitude in this way, will satisfy the exact same algebra. Again, this is just a schematic, but in a second, I will show you one of the simplest examples of this. But now that you have color and kinematics satisfying the same algebra, this allows you to play a game of replacing all your color factors, so removing the color in Yang-Mills and squaring the kinematics. So you're going to now remove this CI and put another factor of this NI. And you're going to say, okay, this is my new scattering amplitude. Now you define this amplitude, you check that it is a physical amplitude, it has the correct poles, it has the correct factorizations, residues where they should be, branch cuts, if you go to loops. And what you find is that it is invariant under linearized diffeomorphisms. So it's a gravitational amplitude. And in fact, it's going to be a scattering amplitude not only of a graviton, but also a dileton and a two-form field. So the low energy limit of string theory. So this is, if you want to think about it in d=4, just a simple idea of squaring of degrees of freedom. So you have 2 degrees of freedom here, you square them and you get 4. 2 from your graviton, 1 from your dileton, and 1 from your axion. So now you have constructed from the square of Yang-Mills your gravitational amplitude. But you can also play the same game, and instead of removing color, you can remove kinematics. So now I remove n and double the color, and I propose this as my new amplitude. And this new amplitude is called the amplitude of bi-adjoint scalars. So these are scalars with 2 adjoint indices that can correspond to 2 different global groups, like 2 different SUNs, for example. And they play an important role in the double copy structure, although they're not really a physical theory. Another important thing of this way of writing the amplitudes is that they're invariant under what's called generalized gauge transformations, which is just the fact that these ends that I'm writing here are not unique. You can shift them by some function, again, of the momenta and polarization vectors, and the amplitude will stay invariant. Of course, this function cannot be anything, so I'll show you in a bit what are the restrictions of that function. Any questions so far? Okay. So this relationship that I'm talking about is not only for Yang-Mills squaring gravity. In fact, we have a web of relationships between different amplitudes, starting from string theory, where you can actually go to the beginning of the double copy story, where you have closed strings as the square of open strings. But also you can descend onto other theories, such as scalar field theories and effective field theories that also have a double copy relation in a very simple example that I will show you next to see this explicitly. But there's another corner of this web of relationships where you can have something like a massive graviton. And this arises from some spontaneous symmetry breaking in your theories. And it's interesting to understand what kind of massive gravity theories can arise from a double copy construction. So let me move on now to show you the explicit example of what these kinematic numerators and color factors look like. For this, I'm going to take the simplest example, which is the scalar field theories. So here you have a nonlinear sigma model, and we're going to construct its square. And it's a theory that's called a special Galilean. Here I'm just showing you what would be the 4-point case. So the quartic interactions, for example, for a nonlinear sigma model will look like this. This you can think of a SUN cross SUN going down to the diagonal SUN. And it gives you a contact term at 4 points. Yes. Yes. In principle, yes, if you could have a double copy relationship for those kind of theories, but it is a very restricted set of massive gravity theories that have a double copy construction, and those don't have the ghosts. So. Sorry, can you speak?
What kind of terms you need to add to the diffraction?
Yeah, so sorry, the question was if it's known what kind of terms you need to have to get these massive gravitons. And what I'm going to show you is a specific list of the theories that we know that can have a double copy construction. Some in higher d equals 4 and higher, and some in d equals 3. So it is known what are the sets of theories that satisfy it. If that's the only set of theories, that's not known. It could be a wider set of theories that satisfy that. Any other questions? Okay, so back to the nonlinear sigma model. So we have this contact term, but I said that we want to write things as a sum of trivalent graphs. So basically, we need to multiply by a 1. Just Mandelstam variable S over S, and now we pretend that this is actually a propagator in the middle, and now we write that contact term now actually as something with a propagator. Once you do that, you can write your scattering amplitude of the nonlinear sigma model in the following way. Your CS, so you're going to have trivalent graphs at 4 points, just S, T, and U channels. So your CS will be these kind of structure constants. CT and CU, you just have to do crossing symmetry, and you can relate them. The propagators, which now I'm writing as the inverse of a matrix, are just your S, T, and U. And your kinematic factors will look like this if you actually go ahead and compute the scattering amplitude here. So basically, now I'm writing what I had before now as a matrix. So just this vector, this inverse matrix, and this vector for n. And you can see that they satisfy this algebra that I mentioned before, so just a simple Jacobi. And the Jacobi, you can write it in terms of a matrix that acts on this vector of your color factors. So at 4 points, again, this is the simplest example. It just looks like this. There's this matrix, accidental vector is 0. If you act with this matrix now on these numerators, you'll see that they do satisfy the same algebra. So you have color kinematics duality, and you're allowed to remove color and put kinematics. Once you do that, you're gonna find this simplified answer that is just ST and U. Now, at every endpoints or check this with. And once you know these amplitudes, you can reconstruct what theory it corresponds to. So at 4 points, you have 4 fields, and it has 6 derivatives. So these kind of interactions. And you can just do this with all the scattering amplitudes, make sure that there's something physical, and you will land on your double copy that is some special theory that has space-time symmetries, and there's some shifts that depends on the fields and also on space-time coordinates. So that's the basic idea of how to do the double copy in the simplest example. Of course, for gravity, it can become a little bit more complicated. So now let's see what happens if you want to include massive mediators instead of the massless propagators that I was talking about before. So the only modification I'm going to do is that this that you had here before and was just a simple Mandelstar variable S, for example, now is a massive propagator. So we're going to do the same. Look at Yang-Mills. Say you have a massive Yang-Mills now. And now check if, well, your color factors will by default satisfy some Jacobi relations. And then you can compute your kinematic factors and check if they have the color kinematics duality. And if so, you could do the double copy. If you just go ahead, do this for a massive Yang-Mills, you will immediately find that this is not the case. So you say there's no color kinematics duality, I cannot do a double copy, and there's just no point in keep going forward, but that's not the case. So what saves you is that you can do generalized gauge transformations to move from something that didn't satisfy color kinematics duality to something that will satisfy it. But this should sound wrong to you because double copy is not something that any theory will satisfy. These are certain special properties of certain theories that should satisfy this. And this procedure will basically take any theory, duality, and then you will build a double copy of any theory. That doesn't mean that the double copy will be physical. So let's understand why. Let's take my kinematic factor n, shift it by some delta n, and assume that it leaves the amplitude invariant, which means that if I put this delta n on this equation here, that should give me 0. And for that, I can use the fact that we have Jacobi relationships. So this MC is equal 0. So I can write delta n at the following form. So this D, M transpose, and some arbitrary vector V. If you plug in that in here, it just gives you 0 thanks to Jacobi relations. So, okay, now I have something that is a generalized gauge transformation under a shift. I do this shift now on this expression for the Jacobi relations of the kinematic factors. Yes. Yes, I think every delta n that will leave the amplitude invariant will have some arbitrary vector that does that. Yeah. The question is if you can actually find this vector and then invert the relation. So, yeah. Kinematics shifts, and you will see that it shifts by this function. So this is just a matrix over here and this arbitrary vector. And you can set it to 0 if you pick your arbitrary vector in the right way. So, okay, we go ahead and do that. And we take these new, let's call them n tilde operators, the ones that actually satisfy color kinematics duality, by choosing this new vector appropriately to have the Jacobi relation. Now the double copy will be with this n tilde, so the shifted ones that satisfy this algebraic relation. And if you express now your scattering amplitude in terms of the original kinematic factors, what you will see is that you have one expression that looks just like the original double copy. So that will be perfectly fine. It has the pole structure of a physical scattering amplitude because it's just given by the poles in Yang-Mills. But then you get an extra term that basically depends on the violations. So this is just the violation of your Jacobi identity of your original kinematic factors. And then there's an inverse of this matrix of the propagators. That inverse of that matrix can give you a physical pulse in your amplitude, and then your double copy is not a double copy of a physical theory. So basically, this could be some random polynomial that gives you some pole at S equal whatever number that is not any mass of the spectrum of your theory. So the question is, what kind of theories actually give something reasonable and physical in here? And this kind of structure was observed before, not only in the massive case, but already in the massless case. And it's the case because finding a correct representation of these ends that satisfy color kinematics duality can become complicated when you do it at higher end point functions or at loops. So people observe this kind of structure in a generalized double copy relationship here, but also it was rediscovered for the massive case here. Yes? Sorry, I couldn't hear. So M is going to be what gives you a Jacobi relationship. So this is the simple example in 4D. In 5D, I think it's a 9x9 matrix that basically just gives you a relationship between your structure constants that satisfy Jacobi relationship. So it's just telling you about the algebra of your SUN. Oh, how do you invert it? Yeah, it generically doesn't have full rank. So you just take a subspace and yeah. Yeah, so actually for the massive case, they tend to have full rank by default. For the massless case, they don't have full rank, and then you have to go to a subspace where you can actually do the inversion. But that's going to be exactly the trick of understanding which theories can satisfy a double copy that's sensible and which don't. So yeah, exactly. That brings me to my next point of how do you avoid having this on physical poles? And basically the answer is that yes, this matrix, when you want to invert it, is known that you don't want to have it full rank. So if it doesn't have full rank, then the matrix will have null vectors, and the null vectors of this matrix will in fact give you additional relationships between the scattering amplitudes of your Yang-Mills theory. And the existence of these relationships is what allows you to have a sensible double copy. So if you have a theory that's massive and comes from some sort of spontaneous symmetry breaking of a massless theory, it's known that this matrix will have what's called minimal rank, which is just the fact that it has the same rank as the massless case. And if it has the same rank as the massless case, for example, at 5 points, it has 4 null vectors, and this leads to 4 so-called BCJ relations, and gives you the standard way of doing a double copy. So you go to the subspace where you can actually invert the matrix, and you check that the this MN that I have here is actually on that subspace where you can invert the matrix, and then you can do the whole procedure of constructing your double copy in this way. So you have to go to the subspace where this is invertible, and this has to be on that subspace. So there have been many examples now of how to do this from a spontaneous symmetry breaking, but there's one new case that we realized a couple of years ago, and is that if you have special case of 3D kinematics, you also have a matrix that's not invertible. And it's reduced the full rank, instead of by 4 null vectors, it will have only 1 null vector. So you reduce to the rank by 1. And this gives you 1 BCJ relation. And the reason for this is because the determinant of this matrix is actually a gram determinant of 4 different momenta. So if you go to 3D, by default, you cannot have 4 antisymmetric vectors, and then the determinant is 0. So with this single relationship between the amplitudes, which is very different to what happens with spontaneous symmetry breaking, we showed that you can get a sensible double copy, at least up to 5 points, and there are no spurious poles, and it factorizes correctly. And the example that we found of a theory that satisfies this is topologically massive theories in 3D. So let me just quickly introduce what are these topologically massive theories. So for topologically massive gravity, what we have is just an Einstein-Hilbert term, but it should have the opposite sign from the standard one, and a Chern-Simons form. And now, of course, it breaks parity, and we're going to have only 1 degree of freedom propagating. So it's 1 graviton, and the spin, if it's plus or minus 2, depends on the sign of your mass term. For topologically massive Yang-Mills, again, you just have your standard Yang-Mills term plus Chern-Simons form, and propagates 1 degree of freedom, and the Chern-Simons level now is proportional to the mass of the field. So in terms of degrees of freedom, what we have here is just 1 degree of freedom squares to 1 degree of freedom. And indeed, we checked that this theory satisfies the double copy for the scattering amplitudes, again, up to 5 points only. And everything seems great, but even already at 5 points, this has to be checked numerically because it's complicated. But I guess the question now is, scattering amplitudes that gives you a non-perturbative solution, because that would be very interesting. So can we? And now it's known that this is possible for certain classical solutions in 4D and higher. And here we show that for these 3-dimensional massive theories, this is also possible. For this, though, we have to introduce the spinorial formalism of 4D and what happens in 3D. Since I'm going to move on to classical solutions, are there any questions on the amplitudes part? Okay, so spinorial formalism. So I'm basically just going to use the fact that your 4D, your Lorentz group, the dotted ones. So, okay, you have this correspondence where correspondence is given by some sort of sigma matrices valued in TSL2C. You can just take the poly matrices and the identity, for example, and you can just reconstruct every tensor that you have now in terms of spinors. And now I'm going to give you the specific example of the Weyl tensor, because this is the one that we're going to use to construct a double copy relationship, aka it's going to be the square of a quantity in now your gauge theory side. So for the Weyl tensor, for example, here, the spinorial quantity will correspond to the following. So you get this term that corresponds to only the self-dual contributions, and this term with the dotted, that is the anti-self-dual. And the structure that you see here with the epsilon tensors just corresponds to what you get out of the symmetries of the Weyl tensor. So again, this is just a translation of the same quantity, but instead of tensors, just with spinors. And you can do exactly the same now in 3D. You start now with SO1, 2, and now you have a subset of these 4D matrices. And since we want to look at what would be the analog of the Weyl tensor, but now in 3D, we want a tensor that can tell you about the conformal properties of your spacetime. So it will be 0 if it's conformally flat. And in 3D, this is the so-called Cotton-York tensor given by the following. And in 3D, since we don't have chirality, every spinor is just undotted. So your Cotton tensor CMU just goes to this CABCD. So the double copy relationship for the exact solutions looks like the following. In 4D, this is known as the Weyl double copy and tells you that the Weyl spinor can be written in terms of 2 spinors of the field strength for Maxwell, because it's going to be a linearized relation, over some scalar. And these components of the Weyl spinor and the field strength should satisfy the equations of motion of your theory. So we're going to be looking only at vacuum solutions. So vacuum solutions of Einstein gravity and the Bianchi basically just translate on this simple equation for your Weyl, and that encodes all the solutions for gravity. For Maxwell, this basically Bianchi plus equations of motion tells you this. And for the scalar, we have that this relationship is actually valid for maximally symmetric spacetimes. So the scalar has a conformally coupled scalar equation of motion. So, okay, we have this relationship in 4D, and what we proved is that the same kind of relationship can be found in 3D for these massive theories. So now instead of having the vial, now you have the cotton spinner being the square of the dual of the field strength, again, over some scalar. And just like it happened that Einstein equations and Bianchi simplify a lot, here Bianchi equations and topologically massive equations now give you this simplified version. Similarly, you can do topologically massive electrodynamics, which simplifies again to this simple equation of motion plus Bianchi. And an interesting fact is that the scalar field is not going to be the conformally coupled scalar field in 3D, but instead it's going to have the same factor as the one that you had in 4D, which tells you that very likely the relationship that you're finding in 3D might arise from a dimensional reduction of the one in 4D, but we don't have a straightforward procedure of telling you, okay, yes, this is how it arises. But it just hints towards it because it's not a conformally coupled scalar in 3D. So I just told you about the scattering amplitudes and about our relationship also for classical solutions. So a big question is, how are these even related? And we know for simple examples that the relationship is the following. So you can get your scattering amplitude and do a Fourier transform that actually is hiding here many things like things being on shell, energies being positive, and so on. But basically the idea is the following. Your vial spinner can be constructed as an Fourier transform of the following object. These are spinors that correspond to the momentum k mu. And this is going to be a 3-point amplitude of a graviton scattering of, for example, a massive scalar. So this 3-point amplitude, a graviton scattering of a massive scalar, will, under this transformation, will. If instead you graph the amplitude of some particle, then you will get a Kerr black hole. So basically now we understand that there's some relationship between what you have here, your scattering amplitudes, and your classical solutions. And you can do exactly the same for Maxwell. So you will get an electric charge of a photon scattering of a massive charged particle. And we know that we have a double copy relation on the scattering amplitude side. So this is a different kind of relation that's called KLT. And it's simplified for 3-point functions. It simply looks like literally the square over the amplitude of the scalar. So since we know that there's this relationship, the question is, how does it imply the relationship for the classical solutions? And the answer is that for certain specific cases, this convolution that you will get from basically just squaring a Fourier transform turns into a product. So there are very simple cases, again, like Schwarzschild black or Kerr black hole or some wave solutions that when you use the fact that you have this double copy here and that they're related by a Fourier transform, then the convolution will turn into a product and you get a simple double copy relationship in coordinate space. So again, the question is what happens in 3D? And it's a bit different than the 4D case. And the answer is that wave solutions will be okay. And we showed in this paper that for these wave solutions, we have a simple double copy relationship. For wave solutions, the cotton spinner and the field strength spinner look in this simple way with some spinor basis O. But if you want to do something like a linearized anion, which will be the analog of what I had here, so scattering of a topologically massive graviton with some massive scalar, then the double copy does not hold. So the question is, why is this the case? And Twistor space is going to help us answer that question. Any questions so far before I introduce twistors? Okay, well, so at the beginning of the talk, as I said, I introduced the double copy in momentum space, so for the scattering amplitude. Then I moved on to a double copy in position space, which, as I mentioned, it holds for some special cases. And we can understand that from an inverse Fourier transform or some scattering amplitudes, and when some convolutions turn into products, which again, just lead you to a position space double copy in special cases compared to the more general momentum space. But there's another space where we can go and check what happens to our double copy, and it's also related both to momentum and position space, which is called twistor space. And we'll see in a second how the relationship works. So I'll show you how there's, instead of doing the full Fourier transform here, if you just do half a Fourier transform, you will get to twistor space and functions that are in twistor space. But there's also something called a Penrose transform that allows you to relate solutions in position space to functions in twistor space. So let me give the very brief introduction to what twistor space is. So you can define a twistor like the following. So first you can think of it as just coordinates on C4. And you can call this like one with a dotted spinner and one with the undotted spinner. Again, they just have opposite chirality. But they should be equivalent on this kind of rescaling. So this indeed is a CP3, not a C4. Now, once you have defined this twistor, you wanna, well, to define projective twistor space, you actually have to define these coordinates in terms of something called the incidence relation, which just means that this undotted undotted spinner will be related to the undotted one through x mu. So this XAA dot is just your coordinate x mu in coordinate space. And these incidence relations encodes basically everything you want to know about twistor space and a relationship between twistor space and coordinate space. So if you start in coordinate space with a point x mu, again, is XAA dot in spinner. Under this incidence relation, you will see that this corresponds to a CP1 that's linearly embedded on this CP3. So it's basically a line. So you just draw it like a line in twistor space, which will be the following drawing. So this x mu here will correspond to this line. Now, if you want to understand the relationship the other way around, so one point in twistor space, what does it correspond to in coordinate space? You can define one point in twistor space as the intersection of two lines. So let's call the point x mu and y mu. And you have the lines corresponding to them, so x and y, and one twistor that is the intersection. If you do that, you will see that for them to intersect in one point, then the x mu and y mu have to be null separated. So basically their expression has to look like the following way. And this is an arbitrary spinner. So if you span all the possible spinners here, you'll see that the relationship is all the possible null planes. So twistor space, you can think about it as just all the set of null planes in your complexified Minkowski, for example. Okay, so now that you have this relation, it is interesting to understand that basically twistor space is telling you something about the conformal structure of your space and given by the holomorphic structures that you find in the twistor space. Now, the more formal way of introducing twistor space is actually through a twistor correspondence. That is what I'm showing you here. So basically, you have the projective spin space, which is complexified Minkowski times a CP1. And there's a double vibration that takes you to projective twistor space and to complexified Minkowski. So this is simply a projection to the XAA dot. Again, it's your x mu, your coordinate. And projective twistor space is going to be your CP3, but actually it's just an open set of CP3. In this case, I'm going to be doing Minkowski, so you just have to remove a CP1, which corresponds to the boundary of Minkowski. So basically, this open space is just corresponding to all the points in your Minkowski space, except for the boundary, so your spatial infinity. Now, we don't care here about the 4D, but it's going to be interesting because we can do a dimensional reduction to understand what happens in 3D. So 3D, which is Mini-Twistor space, can be understood in the same kind of way. So before we saw it was the space of null planes. So here we can think again in 3D as the space of null planes, but now in complexified Minkowski in 3 dimensions. And there's a very simple way of seeing this in this case. So now Mini-Twistor space is defined by a twistor like this with U, a complex number, and lambda alpha, again, just a spinor. The equation of a null plane now can be thought of like this. So n mu will be the perpendicular to the plane, and x mu, again, just your coordinates, and U, just a complex number. If you put this in spinorial notation, you get the incidence relation that's here for Mini-Twistor space. So Mini-Twistor space now has a different kind of rescaling. So the coordinates are not just scaling under R as before, because this equation for the null planes now has to rescale under R squared for U and under R for lambda A, because you have 2 over here. So this is what defines now your Mini-Twistor space. There's another way of understanding Mini-Twistor space, which is basically as a homogeneous space of ESL to C, which are just the isometries of your complexified Minkowski in 3 dimensions, but quotient the group of isometries of null planes. So basically, it's going to be important that this can be thought of as an homogeneous group. Now I said it's also important to see this from a point of view of dimensional reduction. So if you go to the previous slide, I told you, okay, we have this incidence relation in 4D. And here this XAA dot is your X mu in 4D. You can take this X mu in 4D and do a dimensional reduction to the 3D. So you're basically splitting it in an X mu that is in your 3D and the coordinate that's perpendicular. So the one that you're doing the dimensional reduction over. So I'm calling it Z here. So once you do that and plug in this in your incidence relation in 4D, you will find that you get the similar incidence relation that I showed you over here for Mini-Twistor space. So the rescalings are going to be R squared and R as before. And this additional parameter, in principle, it would vanish because you have a contraction of lambda B with lambda B. And the contraction is with the epsilon tensor, so this is basically 0. But there is an additional parameter that will be relevant for the massive case. So now why am I even introducing all of this machinery of twistor space? And the answer is that there is something called the Penrose transform that allows you to get solutions in coordinate space and just from a function in twistor space. So here now I'm going to focus on Mini-Twistors. And I'm going to start here. Let's define F. It's just going to be a function of your Mini-Twistor. And if you want to write a spin n field, you're going to write a field phi with 2n indices of your spinor. And here I'm going to put 2n lambda alphas. And I'm going to integrate this over some contour gamma. So this is going to be just your measure. Now let's understand everything in this Penrose transform. So here, basically this function has to be under the incidence relation. So if you remember, I showed you the correspondence for the spin, for the twistor correspondence. So you start from twistor space and you can go to projective spin space by imposing incidence relation. And then you want to integrate over the fiber to go down to coordinate space. So you integrate over the lambdas, so the CP1. So this contour integral is around a contour on the CP1. And this function you can just think about as a function that has poles in both sides of your CP1 if you want something non-trivial. Now, this function will have certain special properties. Basically, under the transformations that we saw before, this R square of this coordinate U, just a complex number, and this R of the lambda A, so your spinor, it should transform homogeneously in the following way with this rescaling. So this is a -2n minus 2, and this is because we have 2n lambdas over here that will scale with R to n, and 2 lambdas from the measure. So at the end of the day, your field over here in coordinate space should not have any rescalings. But to be more precise, this function in Mini-Twistor space is actually an element of a cohomology class. So this is called the check cohomology. And the reason is because if you could add a function here that only has poles on one side of this contour, then it will give you 0. And if this function only has poles on one side of this contour, it will also give you the trivial field 0. So if you want something non-trivial, your function has to have poles on both sides. And if you add something that just has poles on one side, it's just adding something trivial that doesn't change this integral. Is that clear to everyone? Okay, but so the Penrose transform actually tells you that once you write your function here, there's actually a one-to-one correspondence between these functions, or more actually cohomology classes in Mini-Twistor space, and solutions to the following equation of motion. So this is just like the massless equation of motion that I showed you before. But we wanted something massive for the 3D case, and this is not what we wanted. And the hint is this additional parameter that I was mentioning before. So as I said, Mini-Twistor space can be thought of as a homogeneous space of ESL2C. And now that you want functions of Mini-Twistor space, these actually form a homogeneous bundle, vector bundle. And for that homogeneous vector bundle, in 3D, one of those corresponds to this multiplicative parameter, the R, so the scaling that I was talking about before. But there's this additional parameter that from the dimensional reduction, I mentioned, okay, this is going to be like the plane perpendicular to your dimensional reduction. So under this parameter, they should transform in the following way. So it's this one is a multiplicative, and this is on their addition parameter, and they're all like one-dimensional complex representations of the null planes that corresponds to rotations and translations. You have a different a different set of cohomology classes that are not only parameterized by these parameters R and the homogeneous dimension, but also by this parameter M here, which of course I'm calling M since it's going to be related to the mass. So the one-to-one correspondence, it's now between this class of Penrose transform for functions that transforms in this way, and now satisfy this equation of motion, which is the equation of motion of topologically massive fields. The important part here is what kind of functions satisfy this rule. So an example of a function that satisfies that we found is the following one over here. So we're just expressing it in terms of an exponential with an arbitrary spinor A. This is X, again, just your X mu, lambda, your spinor lambda, and some function of the Mini-Twistors. This is just one example that we found, but it is possible that there are more generic cases. So I will just say that it is an example, and for certain examples, we showed that this could work, and for other examples, we showed that this wouldn't work. So what I'm going to show next is how to apply this exactly to find solutions of these fields. So I'll start with the simple case, which are called type N or wave solutions. And it is actually known that depending on the pole structure of your functions in Mini-Twistor space, you will get different kind of solutions according to the Petrov classification in GR. So wave solutions require a pole structure where you just have a simple pole here, but you also have to be careful to have the correct rescalings and transformation properties of your function. So basically, it should transform in this way. So just choosing a function that transforms in that way and has a simple pole, which is given here by this guy that is a function with a simple 0. You can plug this in your Penrose transform, use the incidence relation, pick some coordinates for your spinor that I'm going to call 1 and z, z being a complex number. And then you will find a explicit expression from your Penrose transform that you can just simply solve. And you can prove that the double copy in position space will hold for this kind of functions, but you also have a double copy relationship in twistor space for this specific class of representatives of this cohomology class. So basically, the gravitational one, that will be a -6. So if you put a n equals 2 here, will be equal to the square of the gauge theory one over the scalar one. Now, if you want to do something more complicated, which in the Petrov classification is called type D, which simply corresponds to the field around isolated objects. So things like black holes or electric charges in the gauge theory. Now, instead of having a pole, a simple pole, now you have to have a 1 plus n dimensional order pole. So you can construct the same class of functions, pick a coordinate, and then you will go ahead and try to just do your Penrose transform, see what you get in coordinate space, and you will find that the explicit double copy relation in terms of a simple squaring breaks down when you try to do this in coordinate space. But for this class of representatives, you still have a double copy in twistor space. So in twistor space, the double copy relationship holds, but now we understand why it breaks when you go to. When you pick these kind of representatives that satisfy a double copy in twistor space and try to perform the Penrose transform, you simply don't get something that squares also in coordinate space. And it's the same as going from momentum space to coordinate space. Before you had Fourier transform, and you needed that the convolution turns into a product. Here you had a Penrose transform, and it's not trivial that the Penrose transform, once you perform it, will give you a simple square again in coordinate space. So there's only special classes of classical solutions where this happens, and it seems that it's only wave solutions and not anything more general like black hole solutions. Yes. Yes, correct. It's just written down on the patch, but again, I'm not entirely sure that this is the most general case. I mean, you need a function that satisfies this property, and we use as an example of a function that will satisfy this property, this representative, but I'm not sure that that's the only representative that's allowed. Yeah. Sorry, I can't see. Yes. I see.
Are the spaces you'll get symmetry reductions
It's not entirely clear to us because we just we didn't write a specific example of what was the space. I guess we just checked if the double copy relationship was holding or not, but we didn't check. Sorry, the question was if this is a dimensional reduction of a tab knot space. And we didn't check explicitly the solution that we're getting, what does it correspond to. There's also one caveat, and it's that I'm talking about type D solutions, and actually type D solutions in topologically massive gravity have been classified, and they're all warped ADS3 type. And here I'm doing the Mini-Twistor of R3. So it's not clear that I should get a reasonable solution of a black hole, for example, because usually the classification tells you it should be ADS. So I don't know if I'm getting something that's not an exact solution, or the exact answer of what you're getting on the other side is not clear to me. Yes. Yeah.
So it's either some number of the points in the research over something
do you mean starting from the Fourier transform to get the? Yeah, this A of A. Oh, no, this X is a 3D.
Yeah, it's a 4D and 3D.
Oh.
That's what it is. And
then I'm literally using this one.
Yeah, it's bigger and of the X of the and sorry, okay.
Yeah.
So in your expression, what you can see that. Oh, sorry. So this would be sorry. Not quite. Sorry.
Okay, well, maybe we can chat about that later. Yeah. Okay, let's see. Yeah, so, well, picking this specific representative, at least, you would not get a simple squaring relationship in coordinate space. What this exact solution corresponds to, I haven't checked explicitly if it comes from my dimensional reduction, which might as well do. And also there's the caveat that exact solutions of this type D have been classified. So it's not very obvious that you should actually have a type D solution that is not ADS3, well, warped ADS3. So I think it's not very clear what these solutions correspond to in general. Could be just a linearized solution. So maybe very briefly, this was just to say that, again, these functions that I'm talking about are actually just some representatives of the cohomology class. So as I said earlier, this function, if you just add something that has poles either just on one side or on the other side of the contour, it would leave your field invariant, but it's also important to notice that it will break your double copy relationship. So the double copy only holds for specific representatives of your cohomology class. And turns out that in certain cases, again, we can relate these representatives to scattering amplitudes. And this is related to this half Fourier transform. So this is the way that, again, this Fourier transform relationship I showed before between some 3-point scattering amplitudes and your exact solution for either your bile, or I guess here it should be your cotton. And now for your vector K mu, I'm splitting it in this way, some omega for the energies and these two spinors lambda. And you can do the same for the polarization vectors. In the massive case, there's something very simple. So once you use that and integrate over, well, your measure of your D3K will turn into this sort of complicated looking expression. But now, instead of integrating over the whole momenta and doing your whole Fourier transform, you can only integrate over, for example, your lambda bars, which is called just performing a half Fourier transform. So if you do that, and here I'm already showing the expressions where I integrated over lambda bar, you will get an expression that looks the following way, where there's some 3-point amplitudes, some factors over your energy, and still to do the integral over the energy. Delta functions that basically just set the energy to be on shell of all these 3-point amplitudes. And the important part is that the scalings with energy, so this is linear, square, or cube, will end up giving you the correct scalings that you need for these Mini-Twistor functions that I showed before. So that simply turns into this kind of cohomology representatives that basically look like what I was showing earlier, with this A arbitrary spinor that arises just from the integrals, but having just a simple pole or a pole of order 2 or 3, depending on which solution you're looking at. So this just tells you that, again, you can relate scattering amplitudes to certain classes of coordinate space solutions, but also this gives you your Mini-Twistor function, and so the specific representative that satisfies a double copy relationship. So let me just conclude by reviewing what I've told you today. So we started in momentum space, just reviewing the basic double copy, where you're required to have the color kinematics duality and specific ends in exactly satisfying this color algebra to do the double copy procedure. Through an inverse Fourier transform, you can get to position space, and only in special cases where convolutions turn into products, you get this simple squaring and bile and cotton double copy. In the same way, you can do a half Fourier transform and now go to Twistor space and get some cohomology class representatives related to the amplitudes that will also square. But more generically, we also see that in Twistor space, the double copy relationship is more clear and is satisfied for certain kind of representatives of these cohomology classes. Now, if you want to go from Twistor space and understand also the position space relationship, you can use this Penrose transform, not only for massless cases, but also for massive cases. So the open questions are, what happens with this type D, where we didn't get a specific clear double copy relationship in position space? And as I was saying before, the type D solutions, so black hole solutions in topologically massive gravity, their type has been classified and there corresponds to warped ADS spacetimes. And it's also still not very clear what's its exact origin through a dimensional reduction, although there are many hints that it's there. So what I'm currently exploring now is the Mini-Twistor space of ADS3 and how you will actually get a double copy relationship there, and if there's a double copy relationship for these warp ADS spacetimes, and also for a Kershey double copy for these spacetimes. So thank you.
So there's time for further questions.
Is there also a zeros copy, like a scalar?
Yes.
What does the mass term? It's just a massive scalar?
Yeah, the mass of the scalar will be the corresponding same mass of the gauge field, same mass of the massive graviton. The only thing is that if you go to ADS or DS, did I show it explicitly? Yeah. You also have this kind of coupling, which is not conformal, but yeah.
More questions?
Thank you for the talk. It's very interesting. Sorry, when you use X on Mini-Twistor space, did you mean the correspondence space, or how exactly are you using X lambda? Because it's no longer obvious how to.
Sorry, when I use X in which one?
On Mini-Twistor space.
Yeah. In this case, I'm just referring to the three-dimensional X, so XAB.
No, sorry, I mean in the transform. Sorry, in the representative that you use.
That X is also XAB, and this A is just some.
So it's not quite on the Mini-Twistor space, but rather on the correspondence space. Is that fair to say?
Yes.
Right. Fair enough. Just checking my understanding. Thank you.
Yes. Yeah, in the sense of it's not just a function of U and lambda alpha, but yeah. It just wasn't clear to me how to write a cohomology class representative of this type only in terms of U and lambda alpha. But I don't know if I'm just not being creative enough. Yes.
Sorry, you start with R4 cross P1, and then you pick out you start with a cohomology class defined on that space, and then you pick out a component of that, and then it splits into these two pieces. So it's not quite on MT. It's more of a component of the thing on PT, but it's got a piece that's on MT. It's got a piece that knows about the extra direction.
Yeah, that sounds reasonable.
Okay, well, let's thank our speaker again.